afternoon. I want to repeat this one. It was without sound. Now, what if I have a capacitor in an AC circuit? And here it is just the source, the AC, with a capacitor. And when the current is going to go into the circuit, that capacitor is going to have its two plates, one charged with Q and the other one charged with negative Q. I don't want to go into the derivation, but in order to find what is really the reactance of that capacitor, we are going to say XC equals 1 over omega C. And you know that omega, it is, okay, 2 pi times the frequency. And therefore, I will say the voltage amplitude across the capacitor is going to be the current times the reactance. We can actually graph it, and you know here that the current is leading. The current is going to start first in the circuit, and then after that, the voltage is going to build on the capacitor, and therefore we can say that the current is leading or the voltage is lagging. Now, just here, I want to show you also that it is, of course, here leading, the current is leading by 90 degrees. And I will say let me draw with a green. Now, for this green here, it is for VL. And it is, okay, the voltage here is leading with 90 degrees. And this means that we're going to have, the current is going to have a delay. And this is from the characteristics of the inductor. Now for the resistor, we're going to find that VR, it is actually in the same, it has the same phase as I. Now, according to what we covered so far, we have different elements here that can be in the circuit. One of them is the resistor, and we represent it as R, and it has that resistance R in ohms, and VR, the voltage amplitude, equals I times R. And of course, here we know that V, which is the voltage at any instant, is in phase with I. For the inductor, we're going to see that for its resistance, or we call it reactance, it is XL equals omega times L, and VL, it is I times XL, and it is leading by, okay, the voltage is leading by 90. For the capacitor C, we have the reactance, it is XC, which is 1 over omega C, and VC equals IXC, and the voltage is lagging by 90. Now for the circuit, which is, we call it a series RLC circuit, we have all the three elements connected together to an AC source. And then according to my diagram, you can say that if I have these three phasors, which are very similar to three vectors, then the total V is going to be the square root of VR squared plus VL minus VC all squared. And then based on this, I can, have my equation V equals I times R squared plus IXL minus IXC all squared. And then I can factor out the I, and from that I can have V equals IC. Now that Z, we call it the impedance of the circuit. It has units of ohms, and as if it's the overall resistance of the circuit. Remember here, we have XL equals omega L, XC 1 over omega C, and we can calculate the phase angle for the overall in using that tan phi equals VL minus VC over VR, which is XL minus XC over R, and phi can be calculated as tan inverse of omega L minus 1 over omega C, because this one here, it is XL, and that one is XC. And then here, if XL is greater than XC, then the source voltage leads the current by an angle between 0 and 90. And if XL less than XC, then the voltage lags the current for the overall circuit. Okay, thank you, and see you soon in another video.